Hello everyone, welcome to another PSAT example. Today we're going to look at the Poisson random variable. So this is one of the primary counting random variables that behaves in a certain way. And we'll just look at the details of this particular example, work through the formula, and see how to use the equation here. So in this example, you are given that cars enter a busy intersection randomly, independently, rate of 4. Now, these are the assumptions of a Poisson, and that is that you're counting something that occurs over time. Usually, it doesn't have to be time. It can be space or distance or length, anything like that. But the occurrences are random and independent of one another, and the assumption is that it's a constant rate. So the question is asking, okay, you have a rate of 4 per second. What's the probability that exactly 6 cars enter in the next second? So what we have here is we're counting the number of cars. I'm going to define my random variable here, number of cars entering. Now, because I'm looking at counting relative to an interval, right? So this is our defined interval. Then this to me implies that X is Poisson. Now, the Poisson, unlike the binomial, has the parameter lambda, and lambda is the rate of occurrence. And so you're given that this is 4 per second. And generally, I like to note the unit of time in the event the question changes the unit that we're dealing with that I'll introduce in the second part of this example here. All right. Alternatively here, this lambda, sometimes books, teachers will use the symbol mu just because the expected value of the Poisson is also mu, and it's also equal to lambda. All right, so again, this is the rate of occurrence. And generally, they're going to give it to you or give you a way that you can calculate it. So all we're trying to figure out is, okay, in the next second, well, what's the chance exactly 6 enter? So the question is asking, how do we find this? So if you recall in your notes, the PMF for a Poisson distribution looks as follows. It's e to the negative lambda, lambda to the x over x factorial. And so your job in these types of problems will be identifying that the random variable is Poisson, and secondly, what is the value of the parameter lambda? And so the Poisson is where you're counting occurrences relative to an interval. Usually that interval is time. And lambda is going to be the rate of occurrence. So you're going to look in the problem to see how you can figure out that rate. Once those two pieces are identified, now it's just a matter of plugging our values into the equation here. So I want the probability of getting exactly 6. I want e to the negative lambda. Well, lambda is 4. I want lambda to the x, which is the particular number we're interested in. So in this case, it's 4 to the 6. And then I have 6 factorial. And that's simply it. If you got a calculator, you can plug all this in and you can check my work here that when I plug this in, I get something a little over 10%. So that's a simple illustration of just plugging the values into a Poisson. Next up, we'll look at changing the unit of time. In the second part of this car example, there's a little twist, and the twist is now changing the interval to 2 seconds. So even though the information in the problem gives us a rate per second, the question's asking per 2 seconds. So this is where the random independence assumption will allow us to go through and navigate. So the original lambda in the previous part was 4, but that's every second. And we want to note this is 2 seconds. So now I've got a different random variable. I have a random variable here. Let's call this one y. Still, number of cars, but now it's every 2 seconds, so per 2 seconds. And that's what I know. And since I've changed the unit of time, this will now scale my parameter. It doesn't change the nature of the random variable because I'm still counting occurrences relative to an interval. But now instead, the lambda I want to use, and I'll subscript here y so we don't confuse it with the first part. This is the lambda for y every 2 seconds is now 8. So if I expect 4 cars per second, then in a 2-second window, because these are independent, I can just scale lambda to match whatever unit of time I want. Second added twist to this particular problem here is now we want, well, what's the chance y is at least 1? So this means, well, it could be 1, or let's write it to be consistent with the previous example. This means it could be 1, or it could be 2, or it could be 3. And here for the Poisson random variable, there is no upper limit. So I could do this forever, which is not going to happen. Instead, I'm going to take advantage of my complement rule and just subtract the complement from 1, and that will give me the same event. And again, the rule, if you recall back from earlier on in the quarter, that we're applying is the probability of an event could be obtained by subtracting the probability of that event's complement. And so if the event I want is all the values from 1, 2, 3 forever, then the opposite of that, the only one I'm not counting, is 0. So to finish, again, this is a Poisson distribution. So I'm going to use the PMF we had earlier. It's going to be e to the negative lambda. So in this case, now it's e to the negative 8. And then lambda raised to the x. In this case, our x is 0. And then over x factorial. And then just a little note here, mathematically here, 0 factorial seems a little weird, but by definition, 0 factorial is just equal to 1. So it's okay to see that. And I'll plug all these in my calculator, so this is pretty straightforward. If I simplify, if you want to look at the algebra, this is just 1 minus e to the negative 8. Since anything to the 0 power is 1, and then we just define 0 factorial is also 1. And then 1 minus e to the negative 8 can be a very high probability. All right, almost 1. What I like to do is just see if this makes sense. So if we expect 4 cars every second, then in the next 2 seconds, we expect 8 cars, right? So the question is asking, well, what's the chance we see at least one of them? It should be very, very, very high. And that's an example of the Poisson random variable.